Welcome everyone. Today we are going to dive into a fascinating world of the nanoscales to discuss one of the most exciting breakthroughs in the material science, quantum dots. You might have heard of them in the context of high-end TV displays, but as we'll see today, their potential stretches far beyond just better screen colors. We are going to see today the potential and how these tiny structures are synthesized, the unique physics that governs them, and how they are revolutionizing the fields from medicine to renewable energy. To understand why these materials are so special, we first need to define what they are and why size matters so much at this level. So, what exactly is a quantum dot? At its simplest, a quantum dots or QD is a nanoscale semiconductor crystal typically ranging from 2 to 10 nanometer in diameter. To give you a sense of a scale, a human hair is about 80,000 to 100,000 nanometer wide. At this incredibly small size, these crystals no longer behave like a bulk materials. Instead, they exhibit unique quantum mechanical properties. There are three key pillars that defines them. First one, the quantum confinement. Because the crystal is so small, the electron and holes are physically squeezed or confined within the nanoscale structure. 2. Artificial atoms. We often call QDs artificial atoms because, like a single atom, they have discrete energy level. In a large piece of metal, the energy level are continuous band. But in QD, you can choose exactly which size levels you want by just controlling the dot size. Third one, size dependent properties. This is the most visible feature. By simply changing the size of the crystal, we can tune its optical and electronic characteristics. This brings us to the core physics of the today's concept, the quantum confinement effect. As a semiconductor crystal shrinks, it eventually reaches a point where its physical dimensions are smaller than the natural spread of its electron. This is the quantum confinement effect. Think of it like a particle in a box model from the quantum mechanics coursework. The equation on the slides describes the energy of these levels. En is equal to h cross square pi square n square by 2m L square, where L is a box dimension. This is the size of your quantum dot. Notice that L is in the denominator and it is squared. This means as the size decreases, energy increases significantly. M represents the effective mass of the particle and N is the quantum number representing the energy level. Physically, this tells us smaller quantum dots emit higher energy light, which corresponds to the blue end of the spectrum because they have larger energy gap. Larger quantum dots emit lower energy light, appearing red because their energy gap is smaller. This is exactly why a veil of 2 nanometer dots looks blue while veil of 6 nanometer dots looks red, even if they are made up of exactly same material. Now we understand the why behind their colors. Let's look at the specific physical and optical advantages that gives us. The magic of quantum dots come from their versatility. Their primary characteristics are all downstream from the quantum confinement we have just discussed. First one, the size dependent band gap. Unlike traditional materials where the band gap is fixed, we can engineer the band gap of quantum dot just by stopping the crystal growth at right time. Broad absorption. Quantum dots are easy to excite, meaning they can absorb a wide range of light wavelengths from high energy UV all the way into visible spectrum. This makes them incredibly efficient light harvester for solar cells. Narrow emission. While they absorb broadly, they emit very specifically. When a quantum dot releases energy as light, it comes out in a very narrow sharp peak. This results in a color that are incredibly pure and vibrant, which is why display manufacturers love them. Color tunability. Essentially, we have color dial. By controlling the diameter during the synthesis, we can hit any color in the visible spectrum with extreme precision. But why are these dots actually sorry? But what are these dots actually made of? Not all quantum dots are created equal. The material composition is just as important as the size because it dictates where the quantum dots can be used. First one, the semiconductor quantum dots. These are the classics like cadmium selenide or indium phosphide. They are like a gold standard for the efficiency and tunability. Though the researchers are moving towards indium phosphide because it's less toxic than cadmium. Carbon dots. These are near green alternative made from the carbon sources. They are eco-friendly and biocompatible. Since they aren't toxic, they are the top choice for injecting into biological system for imaging or sensing. Perovskite quantum dots. These are rising stars in the energy world. They have an incredible high quantum yield, meaning they are very efficient at turning energy into light, making them perfect for next generation solar cells and ultra bright LEDs. Now that we know what they are and what they are made up of, let's talk about how we actually build something so small. Synthesis of quantum dots. Creating something only a few nanometer wide requires extreme precision. We generally categorize synthesis into two philosophical camps. One is top down and another is bottom up. First one, top down approaches. Imagine a sculptor starting with a large block of marble and carving away the excess. In nanotechnology, this involves taking a bulk material and breaking it down using techniques like lithography. The second one is bottom up approach. This is more like a building with Lego bricks. We start with individual atoms or molecules that use chemical reaction to encourage them to self-assemble into nanostructures. This is generally the preferred method because it allows for better control over final size and shape of dots. Let's look closer at the bottom-up chemical methods, which are the most common labs today. The chemical synthesis method. Chemical methods are popular because they can produce monodisperse dot, meaning every dot in the batch is almost exactly the same size. First one is colloidal synthesis. Here the dots are grown in a liquid solution at high temperatures. The solvent contains precursors that react to form the crystals. Because they are in a liquid, they are easy to process and coat into surfaces later. Second one is sol gel method. This involves the transition from a liquid sol, a colloidal suspension, to a solid gel phase. This is particularly useful for creating quantum dots. Composites are oxide based material. Third one is hot injection method. This is the chef's technique for high quality dots. We rapidly inject precursors into a very hot solvent. This burst of concentration creates a massive amount of nuclei, which is tiny crystal seeds, all at once because they are all start growing at the exact same moment. They end up being very uniform in size. While chemical methods are great for liquids, sometimes we need to grow dots directly onto solid surfaces for electronic chips, which brings us to physical synthesis, which is explained by my partner Advait.
Okay, physical synthesis method. What is physical synthesis method? These methods offer high purity and precise control, particularly for integration into electronic devices. An example, atomic spray painting. Think of MBE as a form of high-tech spray painting. MBE means molecular beam epitaxy. Think of MBE as a form of high-tech spray painting, but instead of paint, you are using individual atoms and you are doing it in a vacuum that is emptier than outer space. So how it works? The process happens in an ultra-high vacuum This ensures the environment is incredibly clean, so no dust or air molecule contaminate the material. You shoot beams of pure element at a surface, but like gallium or arsenic. So layer by layer, the atoms land on the surface and stick, building up the crystal one atomic layer at a time. So advantages of this is ultra high purity, atomic layer precision, the operating conditions, ultra high vacuum, and precise temperature control. So why we use quantum dots over here? So because you are building slowly, you can control the exact size and placement of the quantum dots. Since a quantum dot's behavior depends entirely on its size, this control is vital. The vacuum ensures that dots are chemically pure, which is perfect for high-performance electronics like lasers or solar cells, where impurities would ruin the efficiency. Lithography for quantum dots. If the previous method MBA was like building a wall brick by brick, lithography is like sculpting a statue from a block of stone. The slide highlights three ways to do this carving differently, mainly in the tool used. Electron beam lithography. So top-down nanofabrication creates precise quantum dot structures from bulk materials. Okay, which are the different methods? So there are three ways to do this: electron beam lithography, photolithography, and focused ion beam. Right? So what is electron beam lithography? Imagine drawing with an incredibly sharp pencil made of electrons. It is slow but extremely precise, allowing you to draw tiny custom shapes. Photolithography. This is like using a stencil. You shine UV light through a mask to create a pattern. It's faster and better for making many dots at once. Okay, so focused on ion beam. Similar to EBL, but uses ions, heavier particles, to physically mill or sandblast the material away directly. So why we use it, right? The good thing it is reproducible. If you want a neat grid of quantum dots, an array that looks exactly the same every time, like for a computer chip, this is the best method. The bad side, the carving process can be harsh. It involves chemicals and high energy beams that might damage the surface of the quantum dot, making it less efficient than the pristine growth dots from MBE. Surface functionalization and stability. A naked quantum dot is very fragile and sticky. It doesn't work well on its own. The slide explains how scientists put a coat or skin on dot to make it useful and durable. Quantum dot surface chemistry is critically for stability, processability, and application integration. The two main coats. So it breaks into two types of surface layers, ligands and passivation. Okay, ligands. What are they? Organic molecules that stick to the outside of the dot like little hairs. So they act like bumpers. They stop the dots from clumping together so they can float freely in liquids. This is crucial if you want to turn quantum dots into inks or paints. Passivation. Semiconductor coating, right? So a hard shell made of a different semiconductor material of what? Zinc sulfide. So what it does? It protects the delicate core from the environment. A well passivated dot glows much brighter and lasts longer because the shell traps the energy inside where it belongs. Why does it matter? The importance of applications. You cannot put a quantum dot into a TV screen or a biological sensor unless it has the right surface. Need it to flow in a water? What? You should change the ligands. Need it to be a super bright? Add a passivation cell. Applications of optoelectronics. The main takeaway is that quantum dots are revolutionizing screens and light because they produce pure colors and use less electricity than older technologies. Quantum dots revolutionize displays and lighting with superior color and efficiency. An example, quantum dots or QLEDs. Quantum dot LEDs or QLEDs. You have likely seen QLED TVs in stores. This slide explains why they are better. Okay, so QLEDs use quantum dots for precise color conversion, achieving wider color gamuts and high brightness. Instead of filtering white light, which wastes energy and make color dull, quantum dots take blue light and convert it directly into precise or perfect red and greens. You get a wider color gamut and higher brightness without using extra power. Enhanced color accuracy, improved energy efficiency. Okay, coming to displays and lasers. Beyond just TVs and QDs, quantum dots are used for high-tech lighting and lasers. Because you can change the color of a quantum dots just by changing its size. You can tune lasers to the exact color needed. This means the light is very sharp and specific, not fuzzy or washed out. This is perfect for high resolution displays and tiny efficient lasers used in medical devices or sensors. Tunable emission and narrow line width make quantum dots ideal for next gen displays, solid state lighting, high resolution displays, miniature lasers source. Applications in biomedical imaging. Doctors and scientists often need to tag cells or tumors to see them under a microscope. Normally, they use organic dyes, but those dyes fade quickly, like a glow stick running out, right? So quantum dots are different. They are like tiny super bright LED lights that virtually never burn out. Quantum dots revolutionize medical diagnostic and therapy with unique optical properties for advanced biological insights. Advanced imaging, right? The quantum dots are better for taking pictures inside the body for two main reasons. They are brighter and they don't fade. Why they are brighter? They glow much stronger than traditional dyes, allowing doctors to see things in deep inside tissue that were previously hidden. They don't fade. Why? Photostability. You can watch a biological process like a cell dividing for a long time without the light going out. Targeted therapy and diagnostic. Quantum dot just sit there and they can be put into work, right? Finding disease or delivering medicine. They can be coated with special molecule that make them stick only to cancer cells, acting like a spotlight for early detection. Delivering medicine, they can carry drugs directly to a sick cell, releasing the medicine exactly where it is needed. So the challenges are this, like, because many high performing quantum dots are made of heavy metals like cadmium, they can be toxic to humans. Scientists are currently actually working on better coating or using non-toxic materials to make sure they are safe for clinical use. Quantum dot solar cells. Quantum dot solar cells are poised to revolutionize renewable energy, offering high efficient and cost-effective solar energy solutions. Think of a traditional solar panel like a sponge that can only soak up water. If you pour juice or milk on it, what happens? It just bounces off, right? So quantum dots are like a magic sponge that you can just adjust to soak up any liquid. In solar terms, this means they can catch parts of sunlight that normal panels miss. Why are they said as a game changer? Right? So, three major superpowers that make quantum dots solar cells better than the all silicon panels on roof today is tunable absorption and multiple excitation generation, flexible and cheap. Okay, so why? Normal panels struggle with certain colors or sunlight because you can change the size of a quantum dot to absorb any color. You can design a cell that brings up the entire rainbow of sunlight, not just a part of it. In a normal panel, one particle of light knocks loose one electron. In quantum dots, high energy light can knock loose multiple electrons at once. It's like a buy one or get one free. Okay, so flexible and cheap. Why? Normal panels are heavy, rigid, glass slabs. Quantum dots can be dissolved in liquid solution possibility, meaning like we could potentially print solar cells onto a flexible plastic or even paint them onto a car roof. Advanced energy applications and future outlook. The big picture beyond just electricity. While the previous slide focused on what making electricity, how quantum dots will unlock entirely new form of clean energy and become cheap enough for everyone to use, right? Supercharged solar panels, tandem cells is also known as tandem cells. The slide mentions highly efficiency solar and tandem solar cells. What it means, instead of replacing current solar panels, scientists are stacking quantum dots on top of them, enabling next-gen high-efficiency tandem solar cells. That's what. Instead of replacing current solar panels, scientists are stacking quantum dots on top of them. The benefit it's a team effort, like the quantum dots catch the light that the normal panel misses, boosting the total power output significantly without needing a whole new system. Creating fuel from water, green hydrogen production. Instead of making electricity to charge a battery, quantum dots can use sunlight to chemically split water molecule H2O into hydrogen fuel. This creates a clean burnable fuel that produces only water as exhaust, perfect for cars or planes that can't run on batteries alone. Make it cheap and everywhere. Optimize energy conversion. High-tech solar cells are used to be too expensive for normal houses. Because quantum dots are processed in liquid, they have the potential for mass production. Imagine printing solar sheets as fast as printing newspapers. Scalable and cost-effective future. Potential for mass production and widespread integration. That's all for the today's class. Thank you.